This is the second part of the topic of standing waves and resonance. So just as a quick review, we talked about how we could have particular frequencies of waves that would be inside of a specific length, and how the waves would wrap around to fit inside of that length. And those frequencies, the harmonics just meaning a multiple of some base frequency, we would call those resonance frequencies because they wavelengths fit evenly in integer values inside of that length. And the length we saw was based on the wavelength, so the length of the distance in between the two ends is based on the wavelength, the first harmonic being 1/2 the wavelength of the first harmonic, and the wavelength 2 being for the second harmonic, and so on. And our formula that we found was L equals the harmonic number divided by 2 times the nth harmonic wavelength. So let's do some math to see some relationships and how they interrelate. So the definition of a harmonic is actually very simple. Our nth harmonic is equal to n times the first harmonic. So if we want the second harmonic, we just insert 2 for the ends, and that's how we would get our harmonics. Now we had the length is equal to n divided by 2 times our wavelength of the nth harmonic. We can solve this for the wavelength of our nth harmonic, and that's 2 times the length divided by our harmonic number. And we can express that in terms of the frequency of the nth harmonic. That's just the velocity divided by lambda of the nth harmonic, and substituting n for lambda, we get n of the harmonic number times the velocity divided by 2 times the length. Now remember that no matter what the harmonic frequency, the velocity is going to remain the same, because the velocity is not related to the frequencies. It's related to the tension and the mass per length of the string. So our velocity is equal to the square root of the force of tension divided by mu. And our definition of velocity still holds. Remember, we said velocity is lambda times frequency, but we can also express this in terms of harmonics. We can say it's the lambda of the nth harmonic times the frequency of the nth harmonic. And if we put our values for the frequency of the nth harmonic and our wavelength, we'll find that the relationship still holds. The velocity is a constant based on the force of tension and the mu value. Now let's take this velocity function and let's solve for the force of tension. Force of tension is just going to equal mu times the velocity squared. And we can insert our formula for velocity squared, we're going to have mu times lambda of the nth harmonic times the nth harmonic frequency, and because the velocity is squared, we're going to square those. Now we can substitute in for our lambda. And lambda is just 2L over N. Times the frequency. And squared. Now we can simplify. And let's rearrange this. Now this formula is interesting because it relates the n squared value, actually 1 over n squared, to the force of tension. But for L, mu, and frequency are constants. And actually this should be the frequency of the nth harmonic. And so if we were to chart our force of tension related to 1 over n squared, we would get a straight line, and the slope of that straight line would be 4 times L squared times mu times the nth harmonic squared. And we could use this slope to come up with our mu value. And that's exactly what one of the labs, the one on standing waves, is going to have you do. You're going to keep the frequency at some harmonic, and you can find the force of tension by stretching the string, and you can increase the frequency until you get specific antinodes and nodes, and come up with related values and be able to come up with this mu value. Now we can also solve for frequency. And if we solve for frequency, we're going to have, well, we're going to move this part under force of tension. And then take the square root of both sides. Keep forgetting to put my n there for nth harmonic. And then simplify for the frequency, the nth harmonic. And that gives us the square root force of tension over 4 L squared mu times n. So what this is telling us is if we keep our force of tension constant and we vary the frequency based on the harmonic number, we'll get a straight line and the slope of that line will be what's under the square root. And again, we can use that slope to find the value of mu. So the lab is going to have you measure the value of mu using a scale, then calculate mu by changing the tension, and then calculate mu by changing frequency. And this value of mu, they should be very close to each other. You should be able to get within a percent of the actual value. So these are the formulas that you will need for the lab. The force of tension formula and the nth harmonic formula for that to be able to do that lab. And it's a fairly fun lab. I enjoyed it and when I did it to find out the process. You'll find this lab to be very interesting. A lot of fun things to play with.